theorem. And you'll see the importance of this theorem, that how much it is actually, in fact, it is started, you can say, several field, not only of mathematics, of several other branches. You see, it says that if your function, if you take a function f, which is defined on some compact interval, so you can approximate this function by some polynomial. You can approximate this function by a polynomial. Now, the degree of the polynomial may depend on the level of your approximation, that up to which level you actually want to approximate. But whatever level of approximation you want, whatever estimate you want, there must exist a polynomial in such a way that this fx minus px is less than epsilon, for all x belongs to this interval I. So this is very interesting result. आप देखें, कोई भी अगर फंक्शन दिया गया है, केवल कंडीशन आपको चाहिए कि फंक्शन शुड बी जस्ट कंटिन्यूअस ऑन दिस इंटरवल. सो दिस अप्रोक्सीमेशन थ्योरम सेज दैट देयर एग्जिस्ट अ पॉलिनोमियल. आप देखें, पूरा का पूरा जो न्यूमेरिकल एनालिसिस है, आप क्या करते हो कि उसमें कुछ डेटा आपको दिए गए हैं, और आप एक पॉलिनोमियल अप्रोक्सीमेशन वहां पे रखा है कि दिस डेटा इज डेटा ऑफ सम गिवन कंटीन्यूअस फंक्शन. केवल एक ही अप्रोक्सीमेशन आप मान के चलते हो कि हाँ, जो जिस किसी भी चीज का ये डेटा दिया हुआ है वो किसी कंटीन्यूअस फंक्शन का डेटा दिया हुआ, केवल आप ये मान लीजिए. तो यस
सॉरी, बट कोई ज्वाइन करना चाहते हैं.
जस्ट अ मिनट. Yeah. So this is just one I was telling about the this Weierstrass approximation theorem, that any continuous function defined on a compact interval may be approximated or estimated by a polynomial of certain degree. So your whole, you can say, this interpolation, extrapolation, न्यूमेरिकल डिफरेंशिएशन, इंटीग्रेशन, आप जो कुछ भी आप लोगों ने शायद ग्रेड क्लासेस में आप लोगों ने पढ़ा होगा, तो आप क्या करते हैं कि आप एक सर्टेन डेटा की मदद से आप एक पॉलिनोमियल अप्रोक्सीमेट करते हैं, और फिर उस पॉलिनोमियल में आप चाहे इंटरपोलेट करें, चाहे एक्सट्रापोलेट करें, या फिर डिफरेंशिएट करें, इंटीग्रेट करें. होल, यू कैन से, मैथमेटिक्स यू कैन डन ऑन ओनली बेसिस, ऑन द बेसिस ऑफ सम गिवन डेटा. So you only assume one thing, and that is the continuity of the given function. जिस फंक्शन का आप अप्रोक्सीमेशन करते हैं, जिस फंक्शन के बारे में आप जानना चाहते हैं, जिस फंक्शन का वो डेटा दिया गया है, उस फंक्शन पे केवल एक कंडीशन आप एज्यूम करते हैं कंटिन्यूटी का, और बाकी पूरा का पूरा काम आपका ये वेयरस्ट्रास अप्रोक्सीमेशन थ्योरम कहता है. तो थ्योरम में कह रहा है कि अगर कोई भी कंटिन्यूअस फंक्शन, दैट इज अ कंटिन्यूअस फंक्शन डिफाइंड ऑन अ कॉम्पैक्ट इंटरवल, देन देयर एग्जिस्ट अ पॉलिनोमियल such that this fx minus px is less than epsilon for all x in the given interval. Yeah. You can also say that there is a sequence of polynomials. You can say this p and x, a sequence of polynomial, such that this p and x, in fact, so this is a sequence of polynomial of degree 1, degree 2, degree 3, and so on. And this sequence of polynomial uniformly converges to the given function fx. So there exists a sequence of polynomial, such that this p and x converges to the given function f. So this is very, very important result, as just I explained with few examples, and you can say that the whole in some sense, the numerical analysis is a consequence of this Weierstrass approximation theorem. So now the statement, let f be a function from, say, your compact interval is AB to R, be continuous. Now, given a positive epsilon, there exists a real polynomial, a polynomial with real coefficients. There exists a real polynomial Px. There exists a real polynomial Px such that this fx minus Px is less than, strictly less than epsilon for all x in AB. For all x in in particular, there exists a sequence. There exists a sequence of polynomials. This P and X, such that this P and X uniformly converges to fx on this interval AB. So is it okay to everybody? सब लोग इसको समझ गए, इसका स्टेटमेंट थ्योरम?
Yes, sir.
Yeah.
Yes,
so,
sir.
You see the importance of this theorem that only the continuity is given. आप कोई भी complicated फंक्शन आप ले लीजिए, जितने भी फंक्शन को आप न्यूमेरिकल एनालिसिस में आप लोग एप्रोक्सीमेट करते हैं, उसके पीछे बस एक जो कह सकते हैं उसका बैकबोन जो हाइपोथेसिस है कि द फंक्शन शुड बी कंटिन्यू. अगर फंक्शन की कंटिन्यूटी अगर आप ना एज्यूम करें तो पूरा का पूरा सिस्टम आपका फेल हो जाएगा. आप नहीं, क्यों पॉलिनोमियल सम, बहुत सारे ऐसे फंक्शन है जो जिनका पॉलिनोमियल से कोई लेना देना नहीं. इवन एक्सपोनेंशियल फंक्शन, आपका ट्रांसेंडेंटल फंक्शन बहुत सारे, tan इनवर्स फंक्शंस भी बहुत इंटरेस्टिंग फंक्शंस हैं. All those functions are even differentiable, even they are infinity functions, analytic functions. लेकिन वो पॉलिनोमियल फंक्शंस नहीं है. Even rational function is not a polynomial function. But interestingly, any function which is just continuous only can be approximated by polynomial, can be approximated by, ध्यान देंगे कि approximate आप कर सकते हैं polynomial से. ये बिल्कुल just like आप statement जैसे real line पे आप कहते हैं कि any irrational number can be approximated by rational numbers. लेकिन आप इसका मतलब कतई ये ना समझिएगा कि आप उस इरेशनल नंबर को आप रेशनल नंबर के बराबर कर देंगे. आप जितना लेवल तक चाहें, डेसिमल प्लेसेस तक आप चाहें तो एक नंबर को अप्रोक्सीमेट कर सकते हैं. इट डज नॉट मीन दैट अ रेशनल नंबर इज इक्वल टू दैट इरेशनल नंबर. सो इट कैन बी अप्रोक्सीमेट. आप जिस लेवल तक का एस्टिमेशन करना चाहते हैं, जिस लेवल तक का एरर एक्सेप्टेबल है, अप टू दैट लेवल देयर एग्जिस्ट अ रेशनल नंबर, व्हिच इज क्लोज टू दैट irrational number. But it does not mean that irrational number is exactly equal to rational numbers. In a similar way, you should not say that this function fx is equal to that polynomial function. It's not like that. It can be estimated by, मतलब आप जितना एप्सिलॉन चाहें उतना एप्सिलॉन क्लोज हो जाइए, आपको एक पॉलिनोमियल मिलेगा such that fx is as close as the graph of the polynomial. Right? So, okay. So its proof is a little bit tricky and it's involved. So we'll prove using the proof of the Bernstein, a mathematician, and he actually constructed a special polynomial, what is called Bernstein polynomial, and he proved that this Bernstein polynomial, which he constructed for given function f, that is actually a polynomial of certain degree n, and this polynomial uniformly converges to the given function f. So we'll prove. This proof is due to Bernstein. Yeah. So first I'll introduce this polynomial and then we'll come to the proof of this theorem. So what is Bernstein polynomial? Bernstein polynomial. So for a given function f, suppose f is a given function, so we define a polynomial which you may call as this polynomial of degree n, and that depend on this function f, and also this independent variable is x. So you may call bn of x, or only sometimes it is called bnx. So this is the polynomial of degree n, and is defined as, so this is just a definition, you can say. This is just a definition. So for the given function f, this Bernstein polynomial is this k is equal to 0 to n, and this n ck, this function k by n, and x to the power k, and 1 minus x to the power n minus k. So f is given function. F is a given function. So the Bernstein polynomial is defined like this. And you see the importance of this function. But before that importance, first we'll see some consequences. So maybe you can see the consequences in terms of some exercises. Exercise here. So find the Bernstein polynomial on the interval maybe 0 to 1, 0 to 1, for this n is equal to say 0, 1, 2, etc. So for these different numbers, dot dot. For the functions, maybe you can put your function this fx maybe your Bernstein polynomial on this interval. In fact, you can take any interval. It's not necessarily 0, 1, but let us fix this 0, 1. And yeah. So for following functions, n is equal to 0, 1, 2 for the following functions. Yes. Maybe I think we should not write here n is equal to 0, 1, 2. We should erase here. So find the Bernstein polynomial on this interval 0, 1 for the following functions. Say the first function is just a constant function, f0x equal to just 1. And take the second function, f1x is identity function. Maybe third function as simply your x square, etc. So let us calculate. So again, I rewrite this Bernstein polynomial, this bnx or bnfx, which is defined as this nck, k is equal to 0 to n, and fk upon n, x to the power n, and 1 minus x to the power n minus k. So what is bn, say f0x? So let us calculate for f0 is equal to 1. So your f0 is equal to 1, constant function. So this is equal to simply nck, and this is equal to 1. So it's x to the power n, 1 minus x to the power n minus k, and here k is equal to 0 to n. And what is this? What is this? This is nck, x to the power n, 1 minus x to the power n minus k, and k is equal to 0 to n. आप लोगों ने देखा है इसको कभी? ये क्या इसकी वैल्यू इसके इक्वल होगा? इज इट ओके? x to the power n 1 minus x to the power n minus k is just the binomial expansion. Is it okay? So is the binomial expansion of this term
Yes, sir.
1 plus 1 minus x, sorry, x plus 1 minus x. Is it okay? X
Yes,
to the
sir.
power x to the, I think here it should be x to the power k. I'm sorry. It should be x to the power k instead of x to the power n. X to the power k. Here also x to the power k. I think in previous page also it should be x to the power k. Yes, it is correct. So x to the power k and 1 minus x to the power n minus k. So this is just the binomial expansion of x plus 1 minus x to the power n, and this is equal to 1. So therefore, the Bernstein polynomial for this f0 is equal to 1. This constant function is actually the
सर इज इक्वल टू क्या लिखे हैं? x प्लस स्मॉल ब्रैकेट में 1 माइनस x,
x plus 1 minus x to the power n. ठीक है ना?
सर जो ब्रैकेट में है 1 माइनस x उसकी पावर n रहेगा कि ऐसे रहेगा वो?
पूरे का पावर n, the whole
तो
power
सर
n.
ऐसे तो जब उसको खोलेंगे तो सर वो x से x कैंसिल हो रहा है.
So that is why it is equal to 1. तभी तो ये 1 के इक्वल हो जाएगा. What is your a plus b to the power n? What is a plus b to the power n? This is equal to this n c k a to the power k and b to the power n minus k. K is equal to 0 to n. ये एक्सपेंशन आप लोगों ने पढ़ा है कि नहीं इंटरमीडिएट क्लासेज में? दिस इज द बायनॉमियल थ्योरम.
Yes, sir.
Yes, sir.
यहीं पे a की जगह पे हमने x ले लिया और b की जगह पे 1 minus x ले लिया. Is it correct?
Yes, sir.
Okay.
Yes, sir.
Now let us consider this identity function f1x is equal to x. So what is your bn f1x? So this is nothing but this nck and x to the power k 1 minus x to the power n minus k and your fk upon n. So here f1k upon n and f1x is equal to x. So this is simply k upon n. K upon n. And k varies from 0 to n. Right? Is it okay?
Yes, sir.
ये जो है आप यहाँ पे चाहो तो लिख सकते हो f1 k upon n. Upon n is equal to k upon n. So simply this is equal to k is equal to 0 to n and n c k x to the power k and 1 minus x to the power n minus k, and this is your simply k upon n. Right?
Yes, sir.
Okay. Now what you do, can you use this, simplify this expression k upon n and nck. Upon this n factorial k and factorial n minus k. So k cancel out and n cancel out. So numerator you will have this n minus 1 k minus 1 factorial into, you can write n minus 1 minus k minus 1 factorial. Is it okay? So that this is simply n minus 1 c k minus. Is it correct?
Yes, sir.
Okay. So this is equal to power k and 1 minus x to the power n minus k. And now here you see this k varies from now 1 to n. Why? Because for k is equal to 0, you see this term is equal to 0. So therefore, you should start from k is equal to 1 to n. Okay? k is equal to 0 रखेंगे तो 0 हो जाएगा. इसका मतलब अब हमारा k 1 से n तक वेरी करेगा, इसके नाते k इज इक्वल टू 0 पे पूरा का पूरा एक्सप्रेशन 0 हो गया। जब ये टर्म नहीं था तब k इज इक्वल टू 0 पे 0 नहीं था, बिकॉज nc0 इज नॉट इक्वल टू 0, बट बिकॉज ऑफ दिस टर्म for k is equal to 0 it is 0, so you should start from k is equal to 1 to n. Is it correct?
Yes, sir.
Yes, sir.
Right. Now this is equal to, now you take x from here outside, so this will be summation k is equal to 1 to n, and n minus 1 c k minus 1 x to the power k minus 1 and 1 minus x to the power n minus k. Okay. Now what? Now suppose you put here k minus 1 is equal to, say, some other number r. K minus 1 is equal to r. Then what happened? Suppose you put here k minus 1 is equal to r. Then this term after the sigma, so when k is equal to 1, r is equal to 0. R is equal to 0. And when k is equal to n, r is equal to n minus 1. So r varies from 0 to n minus 1. And here k minus 1 is equal to r, so this is n minus 1 cr and x to the power r and 1 minus x to the power n minus 1 minus r. Right? ठीक है ना?
Yes, sir.
अब इसकी वैल्यू क्या हो जाएगी? अगर n माइनस 1 को आप कोई दूसरा नंबर m मान लीजिए, तो अगेन m c r x to the power r 1 minus x to the power m minus r, and r varies from 0 to m. So this is simply again x plus 1 minus x whole to the power m, that is n minus 1, and this is equal to 1. Is it okay?
Yes, sir.
And therefore this is equal to,
Yes, sir.
and therefore this is equal to simply x. सब लोग एग्री कर रहे हैं इससे? And therefore this is simply x. Is it correct? कोई दिक्कत तो नहीं किसी को है ना अभी फिलहाल?
Yes, sir.
Okay.
Yes, sir.
Now next we'll show that this BNF2 BNF2x, where F2 is your F2x is suppose x square. आपने देखा F0 के लिए F0 1 था, उसके लिए so B of F0 this was simply F0, that is 1. B of F1 that is equal to x, F1 xx था. लेकिन अगर B of F2 कैलकुलेट करेंगे, so let us see whether this is equal to x square or something else. So this Bn F2, which is equal to, according to definition, k is equal to 0 to n and n c k and x to the power k and 1 minus x to the power n minus k and f2k upon n. F2k upon n. Or this is equal to k is equal to 0 to n, and this f2k upon n is k upon n whole square. So this is k upon n whole square. You can write k upon n whole square nck x to the power k and 1 minus x to the power n minus k. Right. Now again we'll do some manipulation here. So we start from this expression k upon n. You can write as this, you just add and subtract 1. So this k k minus 1 upon n and plus 1 upon n. You can write k upon n as k minus 1 upon n and plus 1 upon n. And again, you again divide and multiply by n minus 1. So that this is n minus 1 upon n and plus 1 upon n. Right? आप लोग अपने को म्यूट कर दीजिए. Everybody should mute yourself. जब पूछा जाए तब आप लोग केवल अनम्यूट करके जवाब दें. So is it clear? This k upon n is equal to k minus 1 upon n minus 1 into n minus 1 upon n and plus 1 upon n. Now, to break this term, k upon n square nck. So you write this k upon n square nck is equal to this k upon n into k upon n and nck. And you use this k upon n, this formula. So this k upon n and k minus 1 upon n minus 1 into n minus 1 upon n and nck and plus 1 upon n nck. Right? K upon n nck. In fact, you can attach this k upon n to nck. That will be better. You attach this k upon n with n. You have just proved this statement. You see here, k upon n nck. This is equal to n minus 1 ck minus 1. You can use this result here also. So instead of multiplying this with both the term, you just write here. Maybe you can write here this plus 1 upon n and into this k upon n and nck. K upon n nck. You just remove this term from here. So that this is equal to k minus 1 upon n minus 1 and n minus 1 upon n plus 1 upon n. And this term is your simply this n minus 1 ck minus 1. You just use this last result. K upon n is nck is equal to n minus 1 ck minus 1. फिर से इसको यहाँ भी मैं लिख दे रहा हूँ. This k upon n nck, this is equal to n minus 1 ck minus 1. Okay. और exactly इसी फार्मूले को अगर k is equal to k minus 1 और n is equal to n minus 1 के लिए अगर आप यूज करें तो k minus 1 upon n minus 1 n minus 1 ck minus 1 is equal to, this will be n minus 2 ck minus 2. So you again use here, so k minus 1 upon n minus 1 or n minus 1 ck minus 1, this is equal to n minus 2 ck minus 2. So therefore this is n minus 1 upon n and n minus 2 c k minus 2 and plus 1 upon n minus 1 c k minus 1. Is it okay?
Yes, sir.
Okay. Now you use this expression here. ये k upon n square nck की वैल्यू आपने निकाला है ये, तो ये एक्सप्रेशन आप यहाँ पे ले जाकर के रख सकते हैं. Right? So this is equal to, I am directly writing this statement here. We use this relation here so that this expression is equal to, this is equal to sigma, this is equal to sigma k is equal to 0 to n, k is equal to 0 to तो यहाँ पे आप एक चीज ध्यान दे सकते हैं, व्हेन k इज इक्वल टू 0, वो टर्म 0 हो जाएगा. दिस फर्स्ट टर्म विल बी 0, ऑटोमेटिकली 0. When k is equal to 1, when k is equal to 1, this will not vanish. But this term is equal to this term. You see here, is equal to this term. In fact, इसके एक टर्म पहले अगर आप यहाँ पे आए, so this will hold for k greater than 1. But for k is equal to 1, this first term will be 0. For k is equal to 1, this first term will be 0. So basically, you remains with the term for k greater than equal to 2. Right? So you should write here. So maybe I should write k. K is equal to 2 to n, and this term will be your n minus 1 upon n, and n minus 2 c k minus 2, and x to the power k 1 minus x to the power n minus k, right? And plus, is it okay? कोई दिक्कत तो नहीं है ना? यहाँ पे इसको आप क्लोज कर दीजिए. और जब सेकेंड टर्म को आप लिखेंगे तो दिस सेकेंड टर्म इज वैलिड फॉर k greater than equal to 1. So therefore, for second term you can write this k is equal to 1 to n, and then you should write this 1 upon n, n minus 1, c k minus 1. You can do some, this is just intermediate manipulation. This x to the power k and 1 minus x to the power n minus k. Right?
Yes, sir.
Okay, yeah. Now what is this? So this is equal to, when you see here, again you take k n minus 1 upon n outside, and maybe you put this k minus 2 is equal to r, then r varies from 0 to n minus 2, and then if you will calculate finally, so what will you get? So maybe you take, okay, I will just complete here. Let us write. Maybe you can use some other color. So this first term is n minus 1 upon n, you can take outside, and you just take from here x square outside. So what will you get? And k varies from 2 to n. So let us put k minus 2 is equal to r. So this r will be from 0 to n minus 2, and this n minus 2 cr, and x to the power x square you have already taken outside. So k minus 2, and k minus 2 is r, and 1 minus x to the power n minus 2. In fact, n minus k, and you have taken this k minus 2 as r, so k is equal to r plus 2. So you can write n minus 2 minus k, right? So again, what is this? This is simply x plus 1 minus x. Yes? X plus 1 minus x plus 1 minus x to the power n minus 2. So again, this is equal to 1. X cancel, this is equal to 1. So finally, this first term is nothing but this n minus 1 upon n into x square. Simply n minus 1 upon n into x square. And the second term, similarly, you just check just like this first term I did it. So
सर हमारी सी की क्लास चल रही है.
Yes, sir.
I'm just finished within 1 minute. So plus 1 upon n into x. आप लोग इसको कैलकुलेट करिएगा. सेकेंड टर्म जो है दिस इज इक्वल टू 1 अपॉन n इंटू एक्स. तो इस तरीके से आप लिख सकते हैं दिस b nf2 this is nothing but n minus 1 upon n into f2 and plus 1 upon n into f4. तो ये एक्सप्रेशन आप लोग याद रखें और नेक्स्ट टर्म पे इसके आगे हम लोग कंटिन्यू करेंगे. ओके, थैंक यू.
थैंक यू सर.
Thank you, sir.
हेलो सर.
या
सर आज का वो वेबिनार का लिंक सेंड कर दीजिएगा ना.
नहीं, आज का वेबिनार कौन सा?
सर 22 में जो पाई वाला था जो आपने सेंड किया.
अच्छा, ठीक है, श्योर आई विल सर्टेनली डेफिनेटली मेंशन. आज बेसिकली आज 2-3 वेबिनार है, तो मैं उसको फिर से आपको फॉरवर्ड कर देता हूँ. एक वेबिनार तो दिन में ही है, शायद 2 या 3 बजे के करीब है, और एक
मंजुल भार्गव का कब है?
मंजुल भार्गव का शाम को 7:30. उसको आप लोग जरूर सुनिएगा. मंजुल भार्गव का जो है शाम को 7:30 बजे है.
सारे ही सेंड कर दीजिएगा.
हाँ,
अब जो भी वेबिनार है सबका लिंक सेंड कर दीजिएगा.
श्योर. आप लोगों ने अभी हम लोग कल एक संडे को हम लोगों ने वेबिनार कराया था, लग रहा है उसका लिंक आप लोगों को नहीं मिला था, जो आर्टिफिशियल इंटेलिजेंस पे यहाँ पे हमारे सेंटर में हुआ था. तो
मिला था सर, ज्वाइन किया था हम लोगों ने.
ये थे सर हम लोग.
ओके श्योर
सर. तो
और
ये वेबिनार है कि मतलब कोई जूम वगैरह में?
नहीं, शायद मंजुल भार्गव का तो यूट्यूब पे है. यूट्यूब पे आप लोग सुन सकते हैं पूरा वेबिनार. ठीक है, यूट्यूब पे
लिंक सेंड कर दीजिएगा सर.
हाँ बिल्कुल, वो यूट्यूब पे भी है, जूम बहुत सारे जगह वो फैला हुआ है, तो मैं आप उसको सेंड करूंगा, आप लोग उसको देखिएगा. बहुत सारे